Our goal in this tutorial is to give you a broad understanding of how op-amp oscillators work. Also, we will not go into the deep details of the physics of electronic components or equivalent models. But we'll cover enough of the operation of op-amp oscillators to understand how they can be used. In this video, I have reviewed the 10 most op-amp oscillators and introduced square wave circuit. In an op-amp oscillator circuit, an op-amp is configured with a resistor-capacitor feedback loop or inductor-capacitor feedback loop, which triggers the op-amp to go into an oscillating mode, generating a switching on/off pulses from its output pin. The high gain and wide passband of operational amplifier, Opamp ICS, makes it possible for these units to work like an oscillator within a wide range of frequency. The op-amp oscillates immediately as soon as a feedback is employed across its non-inverting input and tweaked to the appropriate amplitude. The IC becomes particularly important in resistance-capacitance-tuned oscillators, because its total gain becomes perfectly suitable to offset the attenuation of the RC network. Additionally, the double input of the differential IC enables not only positive feedback for oscillation, but additionally allows the negative feedback in a few circuits for enhancing the output waveform. A square wave output can be easily generated by forcing an op-amp to oscillate. The indicated circuit combines a Schmitt trigger and an integrator. Consider the scenario. The output is high, and C1 is charged through R3. Because of the resistor divider circuit R1, R2, the voltage at position A is positive 0.9 volt. As soon as the voltage at B gets higher than this, the op-amp's output becomes negative, low. As a result, R3 discharges C1. Once the voltage on C1 falls below negative 0.9 volt, the process is reversed, and the op-amp output returns to its high state. As a result, the circuit oscillates, creating a square wave with a voltage range of positive 10 volt to negative 10 volt. The voltage fluctuations on C1 can be used to determine the working frequency of the op-amp oscillator. This is the collapsed portion of an exponential charge-discharge waveform, but we'll disregard it and pretend it's linear, which it almost is. The frequency may be calculated using this formula. This design uses a dual supply for the operation. For a single supply operation, we can apply this configuration. In the rest of the video, we'll further learn about 7 op-amp IC oscillators, with 3 RC configurations, 3 LC configurations, and 1 crystal setup. These are very common op-amp oscillator circuits which could be applied with pretty much any high-gain operational amplifier IC. Since any op-amp can be used in these configurations, The precise pin numbers aren't specified, except from the standard pins like the inverting input, non-inverting input, input ground, common, and output. The voltage supply pinouts are not indicated, considering that these VCC and V pinouts can change with the specific IC. Wherever feasible, the maximum functional working details is provided for all these basic configurations. Two, Twin-T RC-AF oscillator. The circuit illustrates the resistance-capacitance tuned AF Op Amp oscillator Twin-T null network. This is implemented through the RC network of C1, C2, C3, R2, R3, R4, which decides the frequency level of the output. The op-amp IC needs to have a voltage gain of 60 decibel. This setup is basically an intensely tuned AF amplifier on which a positive feedback is introduced so that it begins oscillating. The Twin-T network is introduced in the negative feedback loop, and since it works like a null network, it helps in eliminating a particular frequency, FR, through the negative feedback. The IC gain gets terminated appropriately at all other frequencies, while FR is conveniently transmitted forward. In this oscillator network, these formulas can be used for calculations. Coupling capacitor C4 blocks the DC current and offers a high capacitance with respect to the capacitors C1, C2, and C3. It consequently doesn't have an effect on FR. Resistor R1 offers a high resistance based on the IC's input impedance and helps to decrease loading of the Twin-T network through the IC input circuit. The inclusion of positive feedback by means of the signal divider R5, R6 results in this very sharply tuned amplifier to oscillate with the frequency FR. When the potentiometer R6 is adjusted to the level where the circuit merely starts to oscillate, output signal distortion is found to be minimal. The Opamp oscillator circuit could be made to work like a continuously tunable oscillator, e.g. from 20 Hz to 20 kHz, simply by replacing the resistors R2, R3, R4 with a 3-gang potentiometer, and selecting capacitors C1, C2, and C3 in trios to adjust the bands. Output control could be accomplished through a potentiometer which may be configured either to the output or introduced between stages of the IC. Three, Phase shift RC-AF oscillator. The phase shift form of tuned resistance capacitance audio frequency oscillator are popular for their extremely low harmonic distortion. In this form of oscillator, RC tuning is achieved through a 180-degree phase shift network configured within the feedback loop of an inverting amplifier. The network consequently generates the precise signal phase rotation for the oscillation. This circuit demonstrates the configuration for a phase shift type IC oscillator. In this setup, the phase shift network includes 3 RC legs in cascade pattern which are identical to each other, C1, R2, C2, R3, and C3 or R4. In this network, C1 equals C2 equals C3, and R2 equals R3 equals R4. All of these legs brings about a 60 degrees of phase shift. The frequency level where the entire shift gets to 180 degrees can be determined through this given formula. To be able to offset the built-in attenuation of the RC system, the Opamp's gain must be around 40 decibel. The Opamp's non-inverting input isn't utilized in this configuration, as it is delivered back to the ground by means of the resistor R1, which can be around 1000 ohms. This Opamp oscillator circuit could be turned into a continuously tunable type in the range of 20 Hz to 20 kHz, simply by replacing resistors R2, R3, R4 with a 3-gang potentiometer, and by switching the capacitors C1, C2, and C3 in trios in order to select the bands. But the circuit's attenuation increases as the values of the resistances is reduced, and this situation could lead to the output signal amplitude going down very fast with frequency, and oscillation may simply stop if R2, R3, and R4 are adjusted to lower values with the high frequencies. Output control could be provided through a potentiometer, which could be either connected to the output of the Opamp oscillator circuit or introduced between the stages of the Opamp. For WIEN-BRIDGE RC-AF oscillator, we have so far learned that the resistance-capacitance-tuned audio frequency oscillators involve 3 resistances and 3 capacitances for the tuning process. However, the Opamp oscillator circuit displayed in figure requires just a couple of resistances, R1 and R2, and a pair of capacitances, C1 and C2, for the same tuning facility. The C1, C2, R1, R2 network forms the 50% of a WIEN-BRIDGE network which, just like the 20 network in Fig, is sensitive to the frequency. The RC configuration is attached inside the positive feedback link on the non-inverting input terminal. In this configuration, C1 equals C2, R1 equals R2, and the frequency response can be determined using this equation. The resistors R3 and R4 does the job of providing the negative feedback that works like a signal voltage divider to the inverting input terminal. This negative feedback helps to reduce the output signal distortion, but it should be implemented with the right proportion by appropriately adjusting R3 and R4. This is important to ensure that it doesn't terminate the positive feedback, leading to the elimination of the oscillation. This form of Opamp oscillator circuits could be easily turned into a continuously tunable oscillator in the range of 20 Hz to 1 MHz, simply by replacing the resistors R1 and R2 with a dual-gang potentiometer, and by ensuring that the capacitors C1 and C2 are switched in pairs in order to adjust frequency bands. The tuning of the oscillator circuit can be implemented over a large frequency range, but its output signal amplitude might show a varying tendency with response to the frequency. Nevertheless, this varying tendency of the amplitude could be decreased using an appropriately dimensioned non-linear resistor, for instance a thermistor, varistor, or double-ended Zener diode, hooked up in between point X and ground. Controlling the output of the oscillator can be executed through a potentiometer, which may be either incorporated into the output or placed between the stages of the IC. (5) Transformer feedback AF oscillator. This circuit displays the basic AF oscillator configuration, where a small audio transformer, T1, is used for providing both the feedback and the tuning which forces the op-amp to work like an oscillator. Any low-gain op-amp IC could work effectively in this configuration. In this oscillator setup, transformer T1 provides the positive feedback to the non-inverting input of the op-amp. T1 transformer can be any form of small transformer. The frequency of oscillation can be calculated through the capacitance C1 and the inductance L of the L1 transformer winding. The given formulas can be used. It is crucial to ensure that the connection of the transformer winding with the circuit is phased correctly for sustaining the oscillation. However, if you find oscillations not working because of wrong transformer winding connections, you may need only one winding of the transformer to be reversed. That's all. Resistors R1 and R2 do the job of applying the negative feedback through a signal voltage divider to the inverting input terminal. This negative feedback helps to minimize output signal distortion, but this must be applied in a properly balanced manner by suitably adjusting R1 and R2. This is important to ensure that it doesn't suppress the positive feedback and as a result destroys the oscillation. The output can be controlled through a potentiometer, which may be in two ways, either to the output or placed between the IC stages. 6. Transformer feedback RF oscillator. The radio frequency or the RF oscillator circuit indicated in Fig is identical to the transformer feedback AF oscillator explained in the previous section, except that in this particular RF oscillator, positive feedback for the oscillation and tuning are supplied through an air-core transformer, L1-Rel2. Any low-gain IC could work effectively in this circuit. In this op-amp oscillator circuit setup, the non-inverting input of the op-amp gets the positive feedback by means of the inductors L1-Rel2 together. L1 can be the winding of a transformer that consists of higher number of turns, while L2 can approximately have 1/4 of the turns in L1. L2 winding needs to be wound closely to the L1 winding, however this coupling does not need to be tightly wound. The oscillation frequency FR can be calculated through the values of the capacitor C1 and the inductor L1. This frequency FR can be determined through these formulas. It is crucial to connect the transformer winding with the right phasing in order to start the oscillation. That said, if you find the oscillations not happening because of a wrong winding connection, you would only require just one winding ends to be reversed. R1 and R2 performs the role of applying the negative feedback to the inverting input terminal of the op-amp by forming a signal voltage divider. This negative feedback helps to stabilizes the working of the op-amp oscillator and minimizes the output signal distortion. But this negative feedback needs to be correctly balanced by appropriately adjusting the values of R1 and R2. This is important to ensure that it doesn't terminate the positive feedback and in the course destroys the oscillation. The variable capacitor C1 can be used for getting a continuous tuning of the oscillator. In order to get a larger range of adjustment, L1 and L2 could be modified as pairs for selecting the frequency bands. (7) Using AF-RF oscillator together. This circuit exhibits an oscillator configuration which uses plug-in type inductors and capacitors for producing both audio frequency or radio frequency signals through a diverse range of frequency. In this Opamp oscillator setup, the positive and negative feedback are used both together. The tuned circuit built using the L1, C1 part connected in the negative feedback loop decides the oscillation frequency of the circuit. Since the L1, C1 works like a wave trap, this tuned stage of the circuit eliminates its resonant frequency, FR, from the feedback loop. The Opamp consequently behaves like a sharply tuned amplifier, becomes responsible for transmitting the frequency FR. However, its gain gets terminated at all other frequencies. The positive feedback, provided by the resistors R1 and R2, which are configured like a signal voltage divider, subsequently enables the op-amp to oscillate at frequency FR. The parameters in this circuit can be calculated using the given formulas. Using a high-value capacitance and inductance together enables the generation of audio frequencies, whereas using lower values of capacitance and inductance enables the production of radio frequencies. The strength at which the oscillation takes place is determined by the adjustment of positive feedback potentiometer R2. Therefore, the R2 allows controlling the level of output signal amplitude. The circuit can work using a number of different op-amps. Considering that output coupling capacitor C2 is required to generate both low and high frequencies, its value must be suitably adjusted to some intermediate value. For example, it can be 0.01 microfarad, unless of course the user is prepared to change this capacitor in addition to L1 and C1. 8. Crystal-controlled RF oscillator. The circuit given demonstrates an op-amp based a crystal-controlled RF oscillator circuit that can work without the need of any tuning. This configuration can operate with multi-stage op-amp circuits with various sensitivity levels. Having said that, it is advised to make use of medium and high-gain op-amps. In this configuration, the crystal works like an exceptionally high Q bandpass filter within the op-amp's positive feedback loop. The positive feedback current transferred through the crystal builds up a voltage drop around resistor R2, which is utilized on the op-amp's non-inverting input pin of the IC. This finally forces the circuit to oscillate with the crystal frequency. Capacitor C1 is utilized simply for blocking the DC content through a capacitance whose value specifically selected for low reactance at the crystal frequency. The input ground of the op-amp, which is common ground, is connected directly to the circuit ground, as indicated in the diagram. The circuit can be also seen having a negative feedback loop, created using the resistors R1 and R3, which constitutes a signal voltage divider network. Negative feedback current flowing by means of this resistive divider causes a voltage drop to appear across resistor R1, which is supplied to the op-amp's inverting input pin. It may be important to adjust the amplitude of this voltage by appropriately setting up the values of the resistors R1 and R3. This ensures that the positive feedback does not get terminated, eventually killing the oscillation. The use of the negative feedback helps to enhance stability of this op-amp oscillator circuit and also helps to minimize the output signal distortion. Nevertheless, this could be totally furnished only when a high harmonic output is needed, for example, in many of the transmitter-type circuit applications. 9. Using MOS Op Amp. A MOSFET op-amp is configured as IC1. As a result, its input bias current is really very low, generally 10 picoampere against 100 nanoampere for a 741. This enables the creation of circuit designs that use extremely little current. An integrator, IC1, and a Schmitt trigger are shown in the circuit IC2. Assume that the Schmitt's output is high, plus 10 volts. R4, R5 have a voltage of around plus 1 volt at their junction. This sends a 1 microampere current via R1, which enables the charging of C1. As a result, C1, IC1's output slopes down at the speed of 1 divided by C, which in this example is 1 volt per second. The Schmitt trigger switches to its low logic state when this voltage hits negative 5 volts. Negative 10 volts. The current subsequently travels in the opposite direction via R1, and the output of IC1 ratchets up at 1 volt per second. This process repeats until the voltage hits positive 5 volts. The upper hysteresis magnitude of the Schmitt. The Schmitt trigger then leaps to its highest output, repeating the period procedure. A square wave, 10V, and a triangle, 5V, are generated by the circuit. The time interval is 20 using the parts indicated. Set R1 equals 10 megaohm for 200 seconds, and R1 equals 10 megaohm, R5 equals 1 ohm for 2000 seconds. Low-frequency IC741 oscillator. Using only a 741 operational amplifier as a comparator, this circuit generates a low-frequency square wave. The frequency may be changed by altering the values of C1 and R4. A decrease in C1 or R4 raises the frequency, whereas an increase in value lowers it. Imagine that the 741's output is low initially, to demonstrate how the circuit works. The inverting input would be at a supply level that is less than half. Assuming that C1 is also uncharged. Due to the current flowing via R4, the bottom end of C1 will begin to drop in voltage until it reaches the value at pin 3. In this situation, T output of the 741, which compares voltages at pins 2 and 3, will turn positive. C1 will repeat the process when the voltage at pin 3 rises to the other side of half supply, forcing the 741 output to follow and generate a square wave.